Welcome. My name is Steve Miller. I'm a math professor at Williams College, and I'm here with two of my assistants. I'm not sure how many more times we'll be able to go to a place with good internet. And our job today is to talk to you about monovariants and invariants. So this is a fun math concept which can be used to solve a variety of problems. So the goal, as you would probably guess, is to explain what this means and how we can use it. It's actually a bit of a mix of math and art. It's a subject where if I show you how it's used, it's not so bad to follow it line by line, but it's often very difficult to look at the problem and come up with, how did anyone ever have the idea to look at it this way? And like many things in life, the more times you do it, the easier it gets. So I will end this video with a really tough, challenging problem that has a very nice answer, and there's a great, not surprisingly, Wikipedia page on it, and there's a great number-filled video. All right, so let's start off with an invariant. So you might notice the word variant embedded in it. So when you think of variant or vary, what does it mean for something to vary? Yeah, it changes. It varies from value to value. So an invariant means not variant. If you remember the movie The Three Amigos, there's famous and there's infamous. Well, they get confused a little bit about what infamous is, but for us, in often means to negate. So it's something that does not change. So I've given three examples of things that don't change. In classical physics, we assume mass and energy are constant. Here's another example. Imagine you're walking on a straight line from 0 to 10. It doesn't matter how many stops you make, the total distance you travel is 10 once you get to the end. It doesn't matter if I stop at 1, at 2, at 3, at 4. But we're going to assume we're just walking in a straight direction. Or I could just stop at the primes, 2, 3, 5, 7.
Could you stop at like 1.5?
You could stop at 1.5. It doesn't matter. You can stop at pi. It doesn't matter how many times you stop. All that matters is that at the end, you've only moved in one direction and that you reached 10. The last one is, imagine you have a meter stick and you bend it in two places to make a triangle. Depending on how you bend it, you can make many different triangles. You could make an equilateral triangle. What other type of triangle could you make? Isosceles triangle? Right triangle? There's a lot of different triangles and they'll have different areas, but they'll all have a perimeter of 1. So a monovariant is a little bit different than an invariant. An invariant never changes its value. A monovariant is a quantity that can change in only one way. It is either non-decreasing, which means it stays the same or goes up, or it's non-increasing. It stays the same or goes down. So here's some examples. The number of pieces on a board in a game of chess or checkers. You don't have new pieces emerging, or you might have a pawn moving to the end and becoming a queen, or you might have a checker moving to the end and becoming a king, but still you don't have a new piece added. The total number of pieces is the same. The score in a sports contest, it's not going to be 3 to 4, and then all of a sudden, no penalty, we're going to take away a point from you. The score only can stay the same or go up.
Like soccer, like there was like a goal.
But then that goal was not official. And so once the official scoring of the play is done, the score is never going to be going down. So your age is a monovariant. In fact, it's strictly increasing at every moment in time you're getting older. Now, do you know something that might not be a monovariant, that might go up and down? Your weight, somebody's weight. You know, when you're young, you start getting bigger and bigger and bigger, which is good. And if you're a lady, you get pregnant. And then you have this really big drop all of a sudden where your weight can go down quickly when you give birth. The last example I gave is the distance traveled by a cannonball, unless there's a very strong wind that's pushing it backwards. All right, so the inspiration for this was a challenge that my son gave himself. Use all 144 tiles in a Bananagram set and have one connected board with every word exactly 3 letters, because he doesn't want to use a 4-letter word. And so a subset of a attempt is listed below. And so the question is this possible? Right. So in the simplest version of the game, the way it worked is you started off with a 3-letter word, and then you always made a new 3-letter word by adding 2 tiles at a time. So for instance, we could start with knit and go from knit to tin, and then knit to tin to knot, knit to tin to knot to zit, knit to tin to knot to zit to own. and on and on and on. So the question is it possible to win placing 2 tiles at a time? And remember, we started with 144 tiles, and we initially placed a 3-letter word on the board. So this is a great time to stop and pause the video and see if you can answer this. So try and see if it's possible. Okay, welcome back. So hopefully you would have realized that it is not possible. So we need to introduce a good monovariant for this problem. So we start, as I said, with 144 tiles. We place 3 down, and then there are how many tiles left? 141. And now here's the big observation. After we place the first word on the board, there's an odd number of tiles on the board. How many tiles are on the board? 3. How many tiles do we have left to place? 141, which is also, and every time we put down a word, we're putting down how many tiles? An even number of tiles, 2 tiles. So after we put down our next 2 tiles, how many tiles are on the board? We started with 3, there's now 5. And after we put down our next 2 tiles,
139.
so after 5, how many tiles do we have when we put down the next word? So the 7. And then when we put down the next 2 tiles, 9. It's always an odd number. So as we said, after we add the 3rd word, that costs us 2 tiles, that'll bring us to 7. So there's an odd number of tiles on the board. In fact, there will always be an odd number of tiles on the board. So while the number of tiles is increasing, if you look at the remainder when you divide by 2, the remainder when you divide by 2 is always 1. There's always 1 tile left. So it is possible to do it, but we have to change things a little bit. We have to allow ourselves at one point to put down 1 tile to make a word. So here's one way to do it. We can start with maybe gel, and then write old. You can write ends. Well, no, I'm sorry. We'll write old. We'll write dem, which is a word. We'll write old, which is a word. Oops. Ems is a word, and that comes in this way, costing us 2 tiles. Gel costing us 2 tiles. Eat over here. But what we can see is we could put down just the E to make the word dem. And then the AT would be another 2 tile there. So by doing this, we now allow ourselves to place 1 tile and make a word. And so here is the board that my son, with a slight assist from myself and the other assistants here today, was able to do. And this is not the only solution, there are other ways. So here is something that my assistants have not seen. It's the checkerboard problem. So consider an 8x8 chessboard. You want to place 2x1 tiles on it so that you cover the entire board. Is it possible? So again, this is a good place to stop and think, is it possible? So I will let you pause the video. Welcome back. So can somebody tell me how you could place a bunch of 2x1 tiles to cover the board?
Row by row. Right next to it.
Yeah, right next to them. So you can just go row by row by row. And again, if you want to, you can spin the tile and you can make it a vertical tile. That's fine. It doesn't have to be a horizontal tile. But you could do the rows one at a time. You could do the columns one at a time. So this is not that difficult of a problem. So we need to modify it to make it interesting. So what we're going to do is we're going to remove the bottom left and the top right corner. So 2 corners are missing. Do you think it's still possible now? Or does the problem at least seem harder? Seems harder. When you have, yeah, yeah.
It should still be possible because there's still an even amount of
Okay,
space.
good. So there's a, well, that doesn't mean it should be possible. It means there's a chance. If we had removed just 1 tile, would it be possible? No. So why can't we remove just 1 tile?
Because then there'd be like an automatic.
There's going to be an odd number of tiles.
Like if you just like put those like there,
So maybe.
and then you put 1 up, then.
Okay, so there's at least a possibility. Okay, so there's at least a possibility. When you have a hard problem, rather than trying to do the hard problem, what should you try to do first?
An easier one.
So what's the easiest, instead of doing an 8x8 board, what's the easiest board you can think of?
1 by 1.
A 1x1. So try to do a simpler problem. First, let's do a one by one. Well, if we remove the bottom left and we remove the top right, if you look really carefully, you will see nothing. The reason you see nothing, yeah, so there's nothing to do. So given that the one by one is a little bit too trivial, what should we try next? A two by two. Well, now when we move the bottom left and the top right, there's no way to even put down a 2 by 2 tile. So let's try a 3 by 3. So 2 by 2s are possible. So let's look at a 3 by 3. Do you think we can do it with a 3 by 3?
No.
No, and if you try to put it down, you'll see very quickly that it can't work. But also, yes?
A 3 by 3 has an area of an odd amount.
Yes.
And so it can't work because there's going to be an extra one.
Excellent. So this was similar to the comment made earlier that there's at least a chance on the 8 by 8 because the 8 by 8 has an even number of tiles, an even number of squares. So with the odd board,
If you only took away one, it would work.
well, then you would at least have a chance.
No, it would work if you take away only one.
Yeah, it would work.
Yes, it would work, yes. So do you think we can do a 5 by 5?
Probably not. Well, no.
No.
Yeah.
In fact, because it'll be an
No,
odd
probably
number.
not.
Right. So we don't have to worry about the odds. So we can try a 4 by 4. So now, again, we're trying to do a simple problem and work our way up to the 8 by 8. So my question is, where do you think we should put the first tile?
Next to the triangle, like it's not possible.
Well, we need to try. I claim that, we have to have this space covered over here, that top left corner, correct? The tile is either heading towards the right, horizontally, or down vertically. Do you agree that we reflect the board through the diagonal, that those two are the same? And then I might as well just assume it's going to the right?
Yeah.
So let's assume that the first one goes to the right, and we're going to show that it can't work. So I've put down a tile, and I've covered up
So
two
now on
squares.
the bottom you could do.
So wait, so now where do we want to put the next tile?
On the bottom, at the bottom.
There's a better spot to put the next tile.
Oh, next to it, because you have to go down.
Yeah, we know we have to cover up in the first row over here, the third spot, that white square has to be covered. So does the tile have to go horizontally or vertically?
Vertically.
It's got to go vertically down like this. Now that we have this, where should we put the next tile?
Again, next to it.
Right next to it,
Has to go down.
where it has to go down like this. Now where should we put the next one?
Horizontal.
Horizontally from the bottom. You see how we're forced to do this. Now where does the next one go? And then up. And uh-oh is right. So we've just shown it's impossible on the 4 by 4.
Which means it's going to be.
Well, not necessarily. Maybe on the 8 by 8.
It's so.
But we would prefer not to have to do this detailed analysis. But at least we were able to do it for the 4 by 4.
That's expensive.
So this is an 8 by 8. So let's think about what happens every time we put down a 2 by 1 tile. What's covered up? 2 squares. Be more specific. Describe the 2 squares that are covered
They're
up.
adjacent.
They're adjacent. What else? Look at the board and tell me what must be
They
true.
cover one black, one white.
They cover one black and one white. So every time you place down a
We're
tile,
missing 2 blacks.
we're missing 2
Black
blacks.
and white. If you put one of those in the top corner and just the top,
On
it would be
also
perfect.
on the 4 by 4, there were 2 whites diagonal from each other.
Yes,
Because the 2 blacks.
exactly. And over here we have 2 blacks now that are diagonal from each other. So we have 2 fewer blacks than whites. And every time we put down a tile, we cover up 1 white and we cover up 1 black. So does this help us?
Yeah.
Yes. Yes, it does. It's
It has-
impossible. Right? So we don't even have to worry about all the different ways of putting it down. And you were saying earlier about trying to zigzag. We know
Yeah.
that can't work.
We could put like one there and say one there. That
You
would
can
work.
use the mouse because people can see.
Like if we put one there
Yes.
and one there, that would still work. Would it?
You mean if we break up a tile?
No.
Oh, so then this becomes an interesting question. So I'm glad you asked this. Whenever you have a hard problem, you always want to say when you're done, what else could I have done?
It's like because that way they're not next to each other and it's covering those
Right.
2 squares.
So here's my question.
So they-
We know that if you have an 8 by 8 board, if you remove 2 tiles, it's impossible if they have the same color.
So what if they don't?
What if they don't? Which pairs of 2 tiles can you remove and still be able to cover the board? And that would become a really good research problem in common drawings. And so I will ask some of my friends if anybody has ever studied this. I don't know this, but I know some. I know some people I can ask.
Okay.
So what I'm going to do now is I'm going to talk about zombies. Now, we should really call it COVID-19 during the present circumstances. So if you are watching this video during the COVID crisis, please make sure that there are no more than 9 other people in your room with you at this time. All right, so here is how the zombie rule goes. So if you share a wall with 2 infected cells, you become infected. And once you're infected, you're always infected. Okay? So I'm going to assume initially that there are 3 zombies. So the 3 red squares are initially infected. Is anybody going to be infected?
Yes.
Yes. So use the mouse and show which ones get infected.
1.
No. Wait, does that get infected?
Wait.
On the next turn, who gets infected? Just use the mouse very carefully.
So wait,
You have to
2
share
are
2. So let him do this when you do the next.
1 and 2.
Right, so just those 2. Now, which ones get infected next?
This guy
That one gets infected?
and this guy.
Yeah, so now we get 2 more infected. Now
Now
it's
my
your
turn.
turn. Now who gets infected?
Unos,
Yep,
Those-
now those corners.
and then that's it.
And then who gets infected?
Nobody.
Now what's nice
Wait,
now,
It will always end up in a square rectangle.
so here's the first conjecture, that you will either always end up in a square rectangle or a union of squares and rectangles. Then maybe they're well separated, right? If this initial square had been lower, we would have had these 4 cells here infected and a small infection over there. So here is a conjecture that when the virus stops, you will be a bunch of rectangles. Now, what's nice here is there is at least some places that are safe. Unlike right now, where it seems like the whole world is under siege, here are some safe areas.
Antarctica is not under siege.
That's true. So
Unless the
here,
penguins do.
right, so here's my first question. Can somebody give me the easiest initial state, okay, that makes sure that everybody's eventually infected? Yes.
Everybody starts off infected.
Yes. So I will use the word smart aleck. You may replace aleck with other things if you want, but this with something from the with something from the grid.
That was
if you look,
unfortunately cut off.
if you look for the
Wait, go back
no,
to the grid.
I will not go back to
Does
the
it
grid.
have
No,
it?
it does.
Wait, I want to see it.
Because this is being recorded. So this is a really good math principle. When you have a problem like this, try to find the simplest, easiest answer. I want to ensure that everybody's is eventually infected. Infect everybody. Okay, that works. It's also very expensive. Imagine each infection costs us money. Can we make sure everybody's infected with having fewer people initially infected?
Take out 1 corner.
So one is take out just 1 corner, and then that will work.
But if I say like
Yes.
the easy switch,
No, those are the easiest way. What's the next thing you could do?
take out 2.
Take out 2,
And
but
so on. But you could do a checkerboard.
you could do a checkerboard. In fact, we've just been doing checkerboard patterns. If we infect a checkerboard, who gets infected on the next moment?
Everybody else.
Everybody else. So notice this is a 50% savings. So yes, wait, don't say, okay. So initially it cost us 64 cells. Now it only costs us 32. A better way of looking at it is if we had an n by n checkerboard, initially it cost us n squared zombies. Now it only costs us 1/2 n squared. But it's still expensive. It's growing quadratically in the number of, in the size of the board.
Here's a money-saving idea. Don't infect anyone.
Well,
Well, then nobody else gets infected.
well, maybe we should look at it the other way, that this is curing, and that we want everybody to become cured. So here's the problem right now. If I were to have a 1,000 by 1,000 board, I would need 1,000 squared, which is 1,000,000, and then half of that, which is 500,000. So the question is, don't say it yet, is there a better way to make sure everybody's infected? This is a great place to stop and pause the video. I should have put the stop sign there, I didn't. So 1, 2, 3, stop. Welcome back. All right. Do you have a way to infect everybody cheaply?
Do the diagonal.
Do the diagonal.
Do the middle.
So if we infect the middle, who gets infected on the next turn?
Everybody kind of use
Use the mouse.
1, 2,
Yep.
3, 4,
Good.
5, 6,
Yep.
7, 8,
Yep.
9, 10, 11, 12, 13, 14.
Right, so what we see is if we infect the main diagonal, on the next turn we infect one above and one below.
And then
And I'll indicate that by the light pink.
and so on.
And then it pushes forward in the next stage, and 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 the next stage. And unfortunately, everybody's now dead. Or zombie.
Or cured.
So now, here's the next question. We just showed if you infect the diagonal, which would be 8 cells on an 8x8 grid or n-1 on an n-by-n, then it's possible to get everybody. What if you only infect n-1 people? So on an 8x8 board, is it possible to cleverly choose 7 squares? So don't say the answer. This would be another great place to have the stop. So here's the grid. So the uninfected grid would look like this. So is there a way to choose 7 cells so that the virus will spread and get everybody? So this is a great place to hit pause and try to think.
There's still
So
no
5, 4, 3, 2, 1, pause. Welcome back. So the infection has spread. Can n-1 infect everybody else? So here is the wonderful observation. So this is the great monovariant. So the perimeter of the infection is never going to grow as the infection spreads. What do I mean by this? So imagine we're looking at this cell in the middle, which is about to be infected because 2 of its neighbors are infected. And we'll assume that these 2 cells are infected, the left and the right, but not the top and the bottom. And I don't care what's going on for all the others. Because this cell is not infected right now, this wall over here, the right wall here, and the left wall here are on the perimeter, the outside of the infection. And these 2 walls, the top and the bottom, are not part of the infection. At this moment in time now, the left and the right walls are now interior walls, and the top and the bottom are now external walls, or the outside walls. And so we see the perimeter of the infection hasn't grown. If we look at this configuration, we see again, these are 2 outside walls, the right one here and the bottom one here. And when it becomes infected, this now bottom one here is now a perimeter wall. This one over here, this right one is now a perimeter wall. And these 2 ones which were outside are now inside. And we see the perimeter hasn't changed. And you can go through the other configurations with exactly 2 infected and see that there's no change. If we had 3 neighbors that were infected, and you can go through the 4 combinations, we see we lose 3 internal walls and gain 1 external wall. So the perimeter goes down by 2. But we lost 3, we gained 1, so there's a net loss of 2. And if we had all 4 neighbors infected, we see the perimeter decreases by 4. So how does this solve the problem? Well, if we have n-1 squares infected, the maximum possible perimeter is if they share no walls, if they're all separate. And what is the perimeter of a 1x1 square?
1.
The perimeter of a 1x1.
4.
The perimeter is 4. If we have 6 1x1 squares, what would the perimeter be?
24.
24. If we had 7, it would be 28. And in general, if we have n-1, it would just be 4 times n-1. And if you just distribute that out, it's 4n-4. But if we take a giant n-by-n grid, what's the perimeter of an n-by-n rectangle?
N-by-n?
Yeah.
Well, that's a square, so
N
squared.
times 4.
N times 4,
Oh, right.
or 4n.
Oh, perimeter. I
The
think
perimeter.
area.
Yeah, and the area would be n squared, but the perimeter would be 4n. So we showed that as time passes, the perimeter of the infection never increases. It either stays the same or it goes down. Let's check this. When we looked at this, what was the initial perimeter here? Well, each square is separate, so it's 4, 4, 4, 4, 4, 4, 4, 4. 4 times 8 is
32.
32. And now if we look over here, it's going to be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then the other half will be the same.
It's still 28.
So it's still 32.
Yeah, the
The
whole
perimeter
square is
never grew. And so we see that since the perimeter never grows, the maximum perimeter of the infection, if we only infect n-1, is 4n-4. The perimeter of the n-by-n square is 4n, so at least 1 square is safe. So there's at least 1 spot to stand where the zombies won't get you. Now what's interesting is if you go back to the board, is it possible to have a cell that has only 1 neighbor?
That's infected?
Wait, like.
Well, we said that there's 1 cell that is not infected.
Yeah.
Right? Is there any cell here that has only 1 neighbor?
No.
No. If you're in a corner, how many neighbors do you have? 2. If you're in the middle, how many neighbors do you have?
4.
If you're on the edge but not a corner, how many neighbors do you have?
3.
3. So everybody has at least 2 neighbors. So even if you were a corner and you weren't infected, if everybody else were infected, would you become infected in the next turn? Yeah, and in fact, we even see that right here. We see that the corner is about to be infected. So when we showed that there's at least 1 square that's safe, there has to be more than 1 square that's safe. Because if there was only 1 square that was safe, it would be infected at the next moment. So the challenge I leave to you is, how many squares must be safe? Must there be an entire row or column somewhere? And if we do have that rectangle result, if that is a true theorem, that the infection must always expand to rectangles,
Or squares.
or squares, but a square is a rectangle, then maybe that is enough to allow us to prove that there must be a row or column somewhere that is safe. And that there must be, like the Red Sea, a parting that separates 2 zombies. All right, so I'm going to end this as the last slide with another possible problem you can look at. It's the Conway checker or soldier problem. And so I've given you a link to Wikipedia and a nice video. And the problem is the following. It's basically you have an infinite checkerboard, and the board is divided by a horizontal line that extends to infinity in both directions. Every line above that is empty, and all the cells below that are filled with checkers. And you can jump over a checker and move up to the next level if there's a space. And the question is, how high up can you move a checker? Can you move a checker 1 unit, 2 units, 3 units, 4 units, 5 units, 6 units, 7 units, arbitrarily high? Well, but then you've got to be able to keep having people move. You can move.
Move the second row up.
So if you take the second row and the second row jumps all of the first row, then there's no way that they can ever move up again because now they're well separated.
No, because then you take the
You try taking maybe the
Then you take the
4th
4.
row and jump, but there's going to be a gap. So I will let people think about this.
Wait, can you only move forward if you jump someone?
You can only move forward if you jump someone. You can't move forward otherwise.
So what I'm saying is, say you have the second round jump the first round, the third round, the second round.
But you can't, no, because once you jump somebody, you're no longer on the board. When you jump over somebody, that piece is eliminated. And that's the problem. So I will leave this as a fun problem. The solution is a bit harder than the zombie paradox, but it all comes down to coming up with a really good monovariant. And these are hard things to think about, but if you can find the right way to look at them, there's a lot of wonderful things you can do. So we hope you enjoyed this lecture. Have a great day. Be safe. Be healthy.